some of you already know me from Twitter. My actual name is Amanda Rousseau. I go by malware unicorn because I thought it was funny, and I like zombie unicorns because why not have like fluffy stuff with like evil stuff together? So what do? I'm a senior malware researcher at Endgame. I look at malware all day. I write detection plugins. On the side, I speak at conferences. I teach malware reverse engineering, and I do this on my own time, so I don't sleep. I'm also on the DEF CON CFP review board, and now I'm on the Optcode review board for Dubai. I host meetups. I have a meetup locally in San Francisco. I follow fashion trends. I started Vanity Sex to follow like cyber and security and fashion. And I occasionally shitpost on Twitter. So, a lot of fun stuff. So, why reverse engineering? I don't know how many of you actually delved into reverse engineering, but it's in a lot of disciplines in cybersecurity. It's one of the foundations of both the red team and blue team. And I've kind of listed out, where reverse engineering might apply in different disciplines. Mainly, I've been on the blue team most of the time, but I've started to venture out into a little bit of red teaming. But you'll see that it's just a foundation. So I thought, wow, I really need to teach people what I know, to teach them in a different way than what they learned in college or what they learn in normal trainings. So what I want to take away out of this talk is look out for rabbit holes. So when I started out, you're looking at the assembly and you're going deeper and deeper and deeper reverse engineering, and you just get stuck. You don't know what you're doing, and you're just focused and hammering away at one thing, and you're spending days and days on it when you shouldn't be, when you should take a step back and break things down so you know what you're doing. So my mentors over the years, I'm not going to say his name, so I'm going to have an anonymous dude, said, you only need a disassembler, a debugger, and a hex editor. You don't need all these fancy tools, all you need is those three things. But fancy tools do help you get by. So I give to you the RE starter pack. So whenever I can't do coffee, I drink Red Bull a lot. I'm always carrying eye drops with me because I have contacts and I'm constantly staring at the screen. I also use x64 debug for my debugger, IDA Pro. I do like Radari too, but IDA Pro is my bae. And then a hex editor. So here's kind of like an overview of tools that you'll probably use, and you've heard of these over the years. IDA, Radari, Capstone is if you want to automate disassembly. Debuggers, like I mentioned before, a lot of people use Ollie Debug because of all the plugins. GDB if you want to do Linux stuff. And then support tools, information gathering. So these are pretty much all the things that I use. I don't use anything else. So that brings me to the approach. Like I said before, the one thing that'll help you go, stay away from those rabbit holes and make things go faster is recognizing patterns. Now that comes with experience. If you look at tons and tons of malware, when I was at FireEye, I used to look at like 50,000 samples a day, which is not enough, right? Not enough time. So I'm here to teach you about, different patterns in a high-level view, but also look at the assembly itself, because it's more like abstract shapes than they are, looking at the little tiny assembly pieces by themselves. So I'm going to break down these algorithms into basic steps. I'm going to tell you that information gathering is key because it'll tell you how everything is structured. And then use the backward and forward navigation. So what do I mean by backwards and forwards navigation? I'm saying start in the middle, then work your way backwards up until you reach the start of the function. And from there you can have your little navigation and where you're going to go next so that you can bring yourself all the way back from the start to the point that you ended in the middle. And take notes. These are my shitty notes. I have like tons of moleskin notebooks at home that just have a bunch of addresses and point little arrows and stuff. So I'm going to go over simple packing, evasion, a couple different evasion techniques, crypto, identifying when there's a crypto algorithm, and then shellcode. So shellcode and packing are almost the same thing, but we'll go into the detail about that. So things to look for when you're looking at packing. Anyone familiar with UPX or the MIDA, any type of those packers, is basically taking the code, making it smaller so that it's in a smaller binary, and then unpacking it in runtime. So when you see packing, it's going to allocate a huge memory chunk, or it'll have that memory chunk there already, it's just empty. It'll load references from a section, a resource, or in the data section. Some routine that loops. This loops a lot, it's obvious. Recreate the import table, which is key because it'll have to put the import table in the new memory section. And then you have to convert that memory section to executable. And then you'll jump to the newly copied bytes, right? So I made it a little animated diagram of what this looks like. So there's a loop happening. There's where the new code's going, recreates the import table, changes that data section to RWX, and then jumps somewhere in the middle where the entry point is so it can do its stuff. All right, UPX. This is really basic. We see it a lot. If you don't want to use a UPX unpacker, I'm going to show you like how it looks in the diagram that I showed you. So in UPX, at this UPX version, this data chunk here, where it's all the junk data that's packed, this is where it's going to put its new data after it's unpacking. Right? So it starts to recreate the import table, and I put these nice little lovely things here. Load library A, get proc address. And a good indicator when something's packed is when you put it into IDA and it'll say, oh, the AIT is fucked up. So that's a good indicator that it's recreating all the imports. And so here's a kind of like a little, is it running? There we go. So I kind of went through, and I did this last night, showing how the imports are being loaded into the new memory location. You can see the 7670, it's all backwards, right? Little Indian. You can see all the imports being loaded with the get proc address and this UPX sample. All right, and then you'll see later on, right down below, it'll call out to virtual protect to change that memory location to executable, and then it'll loop a bit. Remember I said looping? And then it'll jump to somewhere inside that new memory location. So, how to get around it? Look for references to junk data. Anything in the resources, the different sections, or the data, and then look for that jump call, because you're going to want to put a breakpoint on that jump call. Save the addresses of the new if you're debugging, save the address of the new memory location off, put it in your notes, and then set a breakpoint on that memory region in your debugger, and you can jump directly into the code that's executable. All right, now evasion. Don't you like these graphics? I like them. Lots of jumps. Jumps. The whole point of evasion is to throw off the analyst, right? There's going to be a jump that goes directly to the program exit. And then there's going to be a lot of environment checking, as well as a bunch of useless routines to throw you off your course. So here's kind of an example of just a generic evasion. You have some check, and then a jump, if not zero, to exit, and another check, jump to exit, another check, jump to exit. So these checks could be environmental checks, they could be VM checks, doesn't matter. It all looks the same all the time. All right, so here's kind of an example of an anti-VM malware that I have in my RE102 course. You can see, like, after the check, it does a comparison, EAX, EDI, there's a jump, if not zero, or a jump zero, and then here's the process exit that is going to jump to if it's not, if it is zero, and then continue to the next check. So it goes through all these different checks in order to kill the process if it's running in a VM. All right, so there's different types of evasion. And I just explained before that there's VM evasion, where it's checking the environment for VM artifacts. Anti-analysis It uses jumps and functions, useless jumps and functions, anti-AV evasion or anti-AV detection, heavy obfuscation, environment checks, and anti-automation. It just says, I'm looking for user activity. All right. So with VM evasion, what are you looking for? It's going to check anything about the hardware, the BIOS, the registry keys for the hardware stuff. And it's going to look for driver names related to the VMware or VM, depending on what you're using. And a good resource to check that people use is this paranoid fish, pawfish. You can use a script to detect if you're running in a VM. Or you can harden your VM, depending. So in that same anti-VM malware, here is it's where it's checking the physical drive. It's creating the physical drive file so it can check the device I/O control. And this is kind of what it looks like. Here's the call, here's the test, and then jump if not, and then it continues processing. So there's that jump if not 0. Sometimes it's jump 0. You're going to see that often. So normally when you see a registry, an API call or a registry key check, it's doing that environmental check. All right, things to look for anti-analysis. Useless jumps. So this one was fun. If you were to take out all of these jumps, it's push EBP, which is the stack stuff, move EBP, ASP. You don't need all of these jumps, but it throws off AV signatures. So when you look at it even more, it's really tough to follow this in a debugger, but IDA nicely puts this out for you so you can follow along. So on top of that, there's debugger checks, time bombs, and tick timer checks. Tick timer checks is if you start the program and it runs a certain function and it checks the time right after to make sure that it's running properly in a normal fashion, rather than in debugging. All right, anti-AV detection, things to look for. Accessing registry keys for AV names. How many of you have seen this? It'll just sit there and check every single AV it knows to see if it's running. Yeah. And then checking program files, DLLs, and driver names. So if you're familiar with a lot of AV engines, they use a lot of DLLs, and they sometimes inject those DLLs into all your processes. So sometimes it'll check for those DLLs sitting on the image space. And then stack-based strings and IOCs. In that same sample, I have an example of where it's pushing one character onto the stack to build up a whole string. So in this case, it's looking for sample, because it wants to check if its name is sample or its path is named sample, because with VM automation, they're going to name it sample. I don't know why. But you can see SAMPL, and it's pushed and moved nicely into position so it can call it. So this is really hard to write signatures on because they're on the stack and not like in a nice little D-word offset. All right, now anti-automation. This one is fun, and I really hate anti-automation because when I'm reversing it or debugging it, I have to always patch this stuff. So one of the things is mouse movement, checking if the foreground window state changes. So like you just move the window another side, it shows that there's actually someone at the computer. Long sleeps, wait calls. Say your VM automation runs for 5 minutes, it'll run for 20 minutes, so it can go past that analysis time. All right, and then finally, internet connection test. So sometimes it'll go, hey Google, can you see me? Or hey Microsoft, are you there? Because if you can't connect to those, then it says, oh, well, there's something fishy. I don't have actual internet connection. All right, so here's what I explained before, the foreground window state change. So it'll keep going through this loop, checking if the state has changed. And it'll sit there forever until the state actually changes. So when you're doing VM like automation, you're not seeing anything because it's just sitting there waiting for the front window to change. Right. So how to get around it? Like I said, patching is fun. You just have to change, if you're doing it dynamically, all you have to do is change the little 0 flag, or you can patch it directly in the malware, or in the binary itself, and then that way you can run it again. So, and here's that 0 flag I was mentioning. When you're debugging, you just flip that bit to 1. All right, now crypto. Crypto is really easy to detect for strings because there's always going to be a function called right after a string is loaded. So load a reference in data or wherever, call a function right after, loop a lot, XOR something. Really simple. So I'll show you what that looks like. So here in this sample, it's actually going to load encrypted shellcode using RC4 into memory. What you're seeing here is this junk data, small junk data, all this junk data. And then right after it loads this junk data and the size, it calls a function. And you see this function being called a lot because every single time it loads up a string or a byte array, it will call that function and decrypt it. So that's a good indicator, is to see these functions repeated right after data is loaded. All right, so with ciphers and normal crypto, there's a lot of looping involved. It's looping to switch bytes, looping to XOR something, and kind of like an example here, you can see this here is one iteration, one iteration, one iteration. And you're going to see that in these algorithms. So what you're going to keep in mind is finding when you see the increment, do some functions, and keep looping, and keep looping. And you'll see this, and then once it's done going through the whole thing, you know, it will be in that new memory space. And then finally, XOR something. So immediately look for an XOR where there's two values that are different, A, B, not AA. When you see this XOR with two values that are the same, it's just clearing out the register. Just a cheap way to do that. So look for, like here, it's looking at this location at ESI, and it's taking the lower byte of EAX and XORing that together. So this is actually in the RC4 algorithm that this malware was using. Really simple. That's how, you know, have you guys heard of the Flare-on 4 challenge? All I did was look for the XOR, and I was like, oh, it's encrypted. Okay. Now, static analysis. How do you get around it? Frequent uses, like I said, frequent uses of the function right after the data is loaded. And then if you know the crypto algorithm by going through it and writing your notes down and stepping through the whole algorithm, you can create a decryption for that huge memory space, or that huge data that's being referenced. You can place the breakpoint right before it returns to the decrypted area, like you would do in packing, just set a memory breakpoint on the new memory location. Or, I think I just said that. Or you could extract that out, just the data itself, write your script, and then turn that, if it's shellcode, into an exe. And I'll go over that at the end. Oh, shellcode, there we go. It's similar to packing, like I said before. Shellcode is, I'm going to skip ahead here. Shellcode is basically process-independent code. So it doesn't need a specific OS or libraries in order to run. It'll just run by itself. It doesn't need anything else. It may or may not recreate the import table. So that's one of the things I wanted to get across. It'll do virtual alloc, or create a new memory on the heap, turn it to executable with the virtual protect, and then copy that large chunk into the memory, and then jump to the offset or push return to the offset, and then it could spawn a new thread of that new memory location, or just run from that memory location. More often I see the shellcode spawn from a new thread, but in this case it did not. And like I said before, it's similar to unpacking. So here's that nice little lovely diagram again. The shellcode is normally somewhere in data, puts it changes it to RWX, and then executes normally at the start of the shellcode, but sometimes it starts in the middle, but most of the time it starts at the beginning. All right, so here's an example of it starting actually in the middle. It's before, how it gets to the shellcode is not a jump, not like packing, it's just a simple jump, right? So this one is actually pushing that value onto the stack and then returning. So what does that mean? So normally when you want to return to a function, it pops instead. In this case, it's pushing. So when it returns back to that new memory location. So a lot of these look for references in the sections, resources, or data. Look for the jump call or the pop return call, or push return call. I should change that. Save the address, like similar to packing, save the address of the new memory location, put a memory or hardware breakpoint on that new location, and jump to it when it gets executed. Or you can extract the shell code out, decrypt it if it's encrypted, and turn it into an exe so that you can throw it into IDA Pro. And so I think Hexacorn originally had this tutorial where you can turn that ASM into a new exe. I named this section ALMAO, and then here's my shellcode bin that I extracted out from memory, and then I can turn that into an object, and then link it with GoLink, and then I can. But the main thing that you have to do is you have to know the entry point of the shellcode, because if you don't, then IDA is going to be like, well, what the hell is this? What am I looking at? So when you know the entry point, you can go into like a PE editor, and you know that the start of the program starts at 1,000 in hex. You add that with the actual entry point in the shellcode when you're like looking at it, and it should be like 1,000 hex plus whatever your address is, and you put that into the entry point. And then that should allow you to disassemble it and run it in a debugger or a disassembler. All right, finally. Am I on time? All right, things to remember. Take notes. Lots and lots of notes. I think I use Evernote, and all of the reverse engineering stuff I do is just littered with screenshots and like addresses. I mean, I do the notebook too, a tag team. And then patch. I patch a lot of malware if I don't like it. I'm like, well, I don't want to, debug you again, so I'm just going to patch that little instruction so I can run through it nicely and figure out the rest of the binary. And then memory and hardware breakpoints are your friends. I think I explained before about the shellcode and the packing. You want to set a memory breakpoint or hardware breakpoint on the execution of a certain memory or that certain section. That way you can jump to it really quickly and you won't miss it. Loops are annoying, but they're good for identifying a bunch of different algorithms, depending on what type of loop it is, how it's doing its increment. It also might differ based on the language as well, but it's a good place to start, at least for analyzing data that you want to look at. Repeated functions are fishy, but they're great indicators. Like I explained before with crypto functions, you're always going to see that function reused over and over again. I remember there was a malware I looked at where it would decrypt the function before it actually executed it. It's kind of like .NET, where it converts the IL code into machine code, and then runs that function right then and there in runtime. The same thing with like decrypting functions in malware. They're going to decrypt it, decrypt it, run it, and it's kind of obvious that they're reusing the same function. So, finally, questions? No? Sure.
So when you're debugging Linux, do you use GDB as your preference?
Mm-hmm. I have no choice, but yeah.
Well, no, I know, like, can't you use like a remote debugger in IDA or something?
You can if you want to set it up, but, I'm old school and I'll just, turn it on and go at it. I wish I had IDA Analytics, but only in Windows because that's all they'll pay for. Sure.
You mentioned that you run courses. Do you do this online as well?
It's all online already. I'm just not sitting there on video.
Thanks.
Yeah, a lot of the pictures that you saw in there are actually from the RE 101 and 102 courses. Yeah.
When you're looking at so many samples, how do you keep things organized?
I have millions and millions of nested folders. I have backup drives everywhere. No one wants to touch my laptop because it's full of malware. But I can actually show you.
She'll give you a USB key if you want.
Yeah. So I'm super organized, and I have like all my malware here that I'm like recently looking at. And I keep any malware that's old, I like put it on my server so I can go, bring it back down again. It's not password protected, but it's my server and it's locked down, so it's my malware. I do what I want. Yep.
Do you want us to send you samples?
Yes. Yeah. It says, give me your malware. Yeah, I'll look at them. Yep.
Yeah, where's this RE 101 and 102 you were talking about?
It's on my securedorg.github.io. If you go to my Twitter page, it has the URL there. Yep.
The slides are going to be up, right?
Yeah, these slides, yeah.
Yeah, because all that info is on the
Yeah.
slides.
Mm-hmm. Any other questions? Awesome. I think I got everyone back on time now.